Right guys, nice fun video today. We're going to calculate the speed of Will Smith's slap of Chris Rock. In case you haven't seen it, where have you been? I'll show a clip of it now.
that was a nice one. Okay. I'm out here. Richard. Oh, wow. Wow. Will Smith just smacked the shit out of him.
Interesting stuff. So what we're going to do today, we're going to model using parametric equations the position of Will Smith's hand in space, calculate how far it travelled, and in time how long it took, and work out the speed that way, similar to how we did with the car, except the car we assumed it's travelling at constant speed. We're going to assume that the hand is accelerating, but we'll get to that at the end. The first things first, we need to find out how far his hand travelled during the slap. So what I did, I measured myself. Will Smith and I, he's a bit bigger than me, but not by a huge amount. I measured his motion. He begins down here like this, and you can't see it, down here like this, and he comes up like that. His shoulder twists and his arm comes forward in his shoulder like that. Okay, so I model his rotation of his torso. I took the origin as in his neck. Let's draw a graph. If we have our XYZ coordinates as usual in our 3D space, I said this was his neck here, and then his shoulder was here, and his hand was down here like this, and then this is the beginning position, and he swings up, this shoulder comes round a little bit, and the hand comes up here like this. Okay, and here is Chris Rock's face there. Okay, and here's Will Smith there. Okay, so that's his arm, shoulder and arm. First thing I did was measured myself. The distance between my neck and my shoulder joint is roughly, I think I got it as 21, let me check, 21 centimetres. So Will Smith, let's give him an extra centimetre, is a bit bigger, 22 centimetres shoulder. So this distance here will be 22 centimetres. And then I measured my arm, slightly bent, not straight. When you slap somebody, you have your arm bent like this. This distance here to here was 65 centimetres. Let's give Will an extra centimetre, 66 centimetres. Okay. Let's assume Will judge this. He slapped enough people that he knows how far away to stand from somebody when you begin the slapping motion. So we don't have to worry about this distance. Whatever this comes out as, we know Will calculated it correctly in his mind, and it's the right distance. All right. So what we're going to do, we're going to use some parametric equations. When you're dealing with 2 dimensions, you can often put y in terms of x. Okay, so you get y equals x squared. Say you put in x and you get x squared out. Okay. Sometimes the equations are a bit more complicated. You might get the equation of a circle, for example. If we call this a unit circle, so I say that's 1, then the equation of this is x squared plus y squared equals 1 squared, or 1. Again, this is x and y in terms of each other, but we could also, if we want to differentiate or something, this is a pig to differentiate, we could say x equals cos theta and y equals sine theta. Now if we know cos squared plus sine squared equals 1, so it satisfies this equation. But there, in terms of this parameter here, now if we want to find dy by dx here, for example, we can just find dy by d theta is what, cos theta dx by d theta minus sine theta, and then dy by dx equals dy by d theta dx by d theta. Okay, and it's easier to work out than it is having square roots and squares and all sorts of things there. Okay, so what we're going to do, it's also easier to model real life situations if we use parametric equations. So we're going to model these Will Smith's hand using the parameter t, time. All right, so if we look at I'm going to draw it up here just to remind ourselves what it looks like. And we're starting off here. So we're going to start off then there. Now if we look, imagine we're looking from this direction, just at the XZ plane. Okay, so we've got here Z, here X. Okay, we need to go down because we're negative. Now what I said this was 22 centimeters. And what I'm going to do is I'm going to assume this angle here is around about, we'll call it theta for now. It's around about 30 degrees, all right? If you watch the video, he sort of has his hand slightly down and to the side, but slightly out as well. It's about, so 30 degrees, why not, right? What we'll need to find eventually is the x-coordinate in terms of t, the y-coordinate in terms of t, and the z-coordinate in terms of t. T is time, right? We'll go from 0 to 0 being the beginning of the movement and 1 being the impact point, and then we can scale it up accordingly at the end. So first of all, we're going to work out what z of t is. We said theta equals 30. This is 66. Therefore, getting the old trigonometry back, we've got our right angle triangle there. We have this, we want this distance. This is adjacent over hypotenuse. Therefore, cos theta is z over 66. Therefore, z equals 66 cos theta. Theta is a function of t. It will change over time, but for now I'll just write it there as another parameter, okay? Now, we're going in the negative direction, so we want minus there, okay? So that's our z coordinate. Okay, so now we can actually worry about theta. We can say theta of t is equal to, it starts off at 30, and then when t is equal to 1, it's going to be at 90 degrees, okay? So we had 60t as t goes from 0 to 1. It won't be linear in reality. This is a linear function, but we're going to be integrating the curve to find the length of it in a minute. We don't need to know the acceleration speed just yet. We can work that out at the end. There'll be a little trick at the end to work that out. So we're going to use this as our function theta. It's going to make the maths a bit easier early on in the calculations. Okay. Now we want the x coordinate. What we're going to do is get rid of this. We're going to look down from the top. Okay, so now we've got y and x here. So we're coming out 22 centimeters here. And that's, and then to begin with, it's going to be here, and it's going to be, what is it, 66 times sine theta, it would be, wouldn't it? Do you remember our triangle? So at some point in the future, Will's shoulder would have rotated some angle. His torso would have rotated. It goes from about 0 to 60 degrees. We'll call this angle phi, and we can say phi of t is equal to 60t. It starts off at 0 and it ends up about 60. Okay, and then there's going to be, his arm will have moved forward a little bit, so this angle will no longer be 180 degrees. So this distance, his arm's also lifted up a bit. So this distance, this angle is also phi, and this one is called, let's call it whatever that is, psi, is it? We'll call it psi. So now psi also of t is equal to, well, we'll work that out in a sec. We know this distance now is 66 sine theta, and the reason is our original triangle underneath when we had the xz. It's now sticking out. This was 66, this was theta, this is a over 66 equals sine theta, therefore implies a equals sine theta times 66 sine theta, as I put there. So therefore this distance here, this x coordinate, is cos phi times 22, and this bit is cos phi plus psi times 66 sine theta. Therefore x is equal to this first bit, 22 cos of phi. 22 centimeters, that was his arm length, times the angle his shoulders rotated, plus the second bit, 66 times cos phi plus psi times the length of this line, sine theta. I'll write out my theta in a minute, don't worry. Psi of t goes from, well, eventually it ends here like this, and this will be 30 degrees here, and we need to use the sine rule. We know this one is this length is 66, this length is 22, so therefore sine 30 over 66 equals sine this angle k, I've run out of letters, over 22. Therefore when you work that out, k equals 10 degrees here, which means this angle here has gone to 40 degrees. This is 180 minus whatever. Therefore phi starts off at whatever, psi starts off at 0 with his arm straight and finishes off at 40, so therefore it's 40 t like that. Alright. The y coordinate is this distance plus this distance. This distance is this one, so it's 22 times sine of phi, and then it's this distance is 66 sine phi, that's the length of it, times sine of the sum of these angles, sine phi plus psi. Okay, so now we've got our parametric equations for this curve. Let's have a look what they look like. I've plugged them into an online 3D parametric plotter. There it is there, so looks about right, so we're on the right track. Right, I've written them out again. I made a mistake there. It was sine theta. I'm sure you caught it when I did it. Not sine phi that I'd written down. Now what I'm going to do is put theta in terms of phi, just to make it a little bit easier. We can say theta equals 30 plus phi, because phi is 60, and we can say psi equals 2/3 phi. That way we've only got one parameter, makes it a bit easier to write out. Gets less confusing. Our parameter is still t. Phi is a function of t, but rather than write pi t over 3, yeah, we're going to use radians in a minute, guys. Sorry, I'm just going to write phi. Okay, so let's rewrite this. Right, so that's just all in terms of phi. It makes it a bit easier when we differentiate. We are going to differentiate in a sec. That's why I've had to convert to radians. So 60t is pi by 3. It's 60 degrees times t, so it's pi by 3 times t, okay? So what we've got to do now is calculate the arc length. So if you remember how to calculate arc length, you've got your 3D curve here. Some curve like this. We take a small section of it. We calculate the length of that. That's the delta x plus delta y plus delta z squared, all squared. Take the square root, that's Pythagoras' theorem. Right, so if we rewrite this with a delta t outside, we get the square root of, you'll see what I mean in a sec. Delta t, handwrite Matty, delta. That's outside the bracket there. And then we take the limit as delta t tends to 0. This becomes dx by dt. This becomes dy by dt. This becomes dz by dt. And then we sum over all of them. We get the integral between 0 and 1, square root of dx by dt squared plus dy by dt squared plus dz by dt. I can go through all this quicker in another, slower in another video if you want me to explain it, but this is the formula we've got to work out. Now you can see here it's a bit of a pig. I did do it, and we end up with something that looks like the square root of, I have to get my notes, it's 22 pi all squared times 10 over 9 plus 2/3 cos pi by 6 plus 5. Left fine, but remember this is still a function of t. Plus 10 over 9 sine dt. So I think that's the right number of brackets. See if you can get there. So you've got to differentiate this, square it, differentiate this, square it, differentiate this, square it, add them all up, do a lot of cancelling, see if you can get to this point. You can't integrate this doesn't go, it's not analytic, we have to use numerical methods. What we're going to use is the trapezium rule. The trapezium rule approximates an integral. You've got some foot curve here. By making trapezia, you get this point here and this point here, say h apart, and you get this point and this point. This is another h. Each of these are h units apart. So you want to calculate this area, and you draw a trapezium. So this is slightly overestimated it, but this one's underestimated it. The area of a trapezium, if it's A, B, and H, is equal to half A plus B. So you sum all the trapezia and you get an approximation for the area. Now I wrote a bit of Python code to do that. It wasn't too hard. I'll leave that. I won't bother putting it in the description. We came up with an answer of, with 10 trapezia, you get 137.187. 7. With 100 trapezia, you get 273.31. 1,000 trapezia, you get 137.2739. So yeah, this is accurate enough, right, for our needs. Wolfram Alpha, if you put it in, will give you a value of 137.274. So yeah, we were close enough with this, to be honest. But anyway, that's the distance of the arc. That's how far his hand travels in a certain amount of time. Now if we have a look back at the footage, the slow-mo footage, I'll put it on the screen while I'm erasing this. I've counted the number of frames from when he first pulls his hand back ever so slightly to when he impacts the face of Chris Rock. Now if you can see, it's 5 frames. Now that video is running at 24 frames a second, so it took 5 out of 24 seconds to travel that distance. Now if it's traveling at constant speed, we know from our speed distance time, we know that speed is equal to distance over time, and that is equal to 137 over 5 over 24 equals 24 times 137 over 5 equals 657 centimeters per second. That's 6.57 meters a second. That's if it's traveling at constant speed, but it doesn't. It starts off at 0. If we draw a graph of time versus speed, This is 6.57 meters a second. This is constant. This is our time, 5/24 seconds. Okay, but what we're doing, we're going to assume that it's got constant acceleration. Therefore, it's a constant, a straight line up like that. The speed increases linearly. Now the area under the speed is the distance. So this area here, this rectangle, has to be the same as this area under this triangle. So you can see that the final speed is twice the speed. So twice 6.57 equals 13.14. And that's meters per second, which in kilometers an hour is 47 kilometers an hour, is equal to 29 miles an hour. And there's our answer. So, I mean, that's pretty fast, as fast as a car, right? I certainly wouldn't want to have been in Chris Rock's position at that point. Now we did a lot of work there with the parametric stuff and the trapezium rule and stuff. We could have just assumed it was a circle. Imagine he starts here and just goes boom like that. A circle with radius 66 plus 22, that's 88. So diameter is 176 times pi is whatever that is, and then divided by 4 because it's a quarter of the way around, and that would have given us an answer of 138 centimeters. So virtually the same, right? So it's a lot of work for not much of an increase in accuracy, but it's good fun. So hopefully you enjoyed that, and I'll see you next time.